Welcome back to the orientation for clinical research. Now we're going to talk about data management. Because once you've collected your data, you have to do something with it, and you should be prepared ahead of time for how you will organize, manage, share, and securely store your data. Two things that you should know about data collection is the importance of consistency and the tools that you can use to make sure that your data collection goes smoothly. As far as consistency goes, it's important that if you have a team of people doing data entry, that they are trained to do it properly, to follow your instructions, to know what goes where. You should also have a data dictionary, and we'll talk a little bit later about what that means. Secondly, with using tools, it's important to know what is available to you. Many people just use a spreadsheet. So they'll open up an Excel spreadsheet and they'll put their data in there, but there are other tools available. REDCap in particular is one that's quite useful for clinical research. It is HIPAA compliant, meaning that you can store private health data there. It also has survey features, so if you are combining surveys and other forms of data, or if you're just doing surveys yourself, you can use the REDCap tool to distribute those surveys. Some clinical trials will also develop a custom app. This is actually not that expensive these days and may be helpful if you need to do quite a lot of data collection or if you have a large number of people. The app can help you to organize who is collecting data where and how they're doing it. You could have it for participants to enter information on their own. So this can be a very useful tool for you. If you are using a spreadsheet, we need to talk about how you structure your data. And there are a lot of different ways that you can use a spreadsheet. But if you are planning to do any sort of statistical analysis, there is an important way to structure your data to make it easier for the statistician or for the analyst to use. The first thing you need to know is to make it rectangular. You should not have extra rows or extra columns off the end. You should have each column representing one variable. So this may be a blood pressure reading. This may be an answer to a single question. Each column should be only one piece of data. And each row is therefore one observation. Now, there's a difference between long and wide format. When we talk about long format, we mean that each row is a single time point for a single participant. So if you have multiple time points for a participant, you may have multiple rows for that participant. Whereas a wide format, you have one participant per row and then multiple columns representing different time points for each variable. Because each column is one variable and each row is one observation, that means that each cell is a single data point. There should not be empty cells. You should have something to put in. If a particular measurement was not taken, you should have a code that you use to put in to say this is a missing data point. Personally, I prefer NA. Some people do a dash. Some people write missing, but you should have something consistent that you use to recognize that there is a missing data point. You should also only have one thing per cell. If you find yourself needing to use commas or semicolons to separate out data points within a cell, you either need a second column or you need a second row. So you need to make sure that each cell represents a single data point. And finally, keep your raw data spreadsheet simple. Do not do calculations in the raw data. If for instance, you are going to be calculating BMI, you will want a column to represent height and a column to represent weight, and you will calculate BMI in your calculations in your analysis, not in the raw data. Also, do not use formatting as data. Colors, bold, italics. That is not a format to use for indicating actual information. All information should be represented with words or numbers, one per cell. Avoid empty columns and empty rows. Analysis software really hates those. When you're organizing your data, there are some hints from data management that can be very helpful for keeping track of where you are. First, naming conventions. How you name your files and folders, make sure that they're descriptive, that you don't just name a file or a folder data, because you may have multiple projects and then you won't know which data that is. So make sure you have a descriptive name that you can use, and if possible, include dates. Don't name files or folders using spaces or characters. A lot of programming languages really don't like spaces. I use underscores instead of spaces or characters. Some people use dashes. Don't use periods. That can be confusing. Keep your names short. So they should be descriptive, but you don't want long names or long paths where you're going 5 or 6 long named folders deep to find your file. It's easier if you keep your name short so that you can keep track of where things are without having to write a whole paragraph to find your file. And be consistent with your naming. So if you use a particular name for a study, use the same name for every version of that database. And if you have multiple spreadsheets associated with a study, it's nice to start the name or end the name with a common prefix or suffix, just to keep track that this is all part of the same study. Now, when I talked about versioning, versioning is what we use to talk about keeping track of different versions of a particular file. I like to use my naming conventions to include version. So some people do underscore V1. I end each file name with underscore and the date in which I last manipulated that file. And I always do the date with the 4-digit year, 2-digit month, 2-digit day, because that way, if I sort alphabetically, I will see very easily what the earliest and what the latest dates are. I do not recommend the use of final in a name until you have either frozen the data set, meaning you are taking in no more data, or you have published the paper, meaning you're not making any more edits to that manuscript. If you are working on a large project with a lot of people, or if you really want to keep track of what different versions of files or data sets are, there are things called Git or GitHub or Subversion. These are programs where you can keep track of every version. It's helpful, especially with large group projects, especially with coding. These are very common, but it's also helpful because you can share files that way. It's not necessary. There are other programs that use versioning. I know Box Storage has a versioning. It's just a helpful way, especially if you're working on a group project. Now, I mentioned Data Dictionary. A data dictionary is a file that describes your data sufficiently that you know what is in the data and that you can follow along with all of the data points, all of the columns, what the rows represent. So in a data dictionary, for each variable, you would have a definition, you would have a description of how it was collected, and you would have some sort of description of what each of the codes mean or what the units were, anything you need to know to understand what that variable is. Here on the right, I have an example of a more casual data dictionary. This is actually from a data set that was shared with me by a mosquito control district. And you'll see that the first point is how the data were collected. So it's describing to me what standard elevated traps are, what gravid traps are, and how the timing of the collection was. And then for each of the variables that is not obvious, it has a definition of what that variable name means and what the possible outcomes of that variable are, such as in the first, the zone, 1 equals full control and 2 equals unlikely to receive full control. That helps with understanding what these codes mean. Now, this is a very simplified data dictionary. So things like date, latitude, longitude, those are not defined here because it was assumed that I would know what they meant and that I could reach back out if I had questions. Here is a more precise data dictionary, and this is from another project that I was involved in. And you'll see that they used a spreadsheet for this one that can be very helpful for a data dictionary. In fact, this spreadsheet was another page within the spreadsheet that included the data. That means that when I got the spreadsheet with the data, I also got the data dictionary, which made my life so much easier as an analyst. So you'll see that there's a column for the variable name, a column for the variable label, so what they would label that variable as, a description of what exactly that variable meant, a column for units when appropriate, a column that tells me what type of variable it is. So it tells me, is it supposed to be a text, a date, numeric, or categorical? And then for the categorical, there's a column with categorical options that shows me what the options are. And in the description, you'll see down in death YN, this is whether a patient is known to be deceased, yes or not, N. And it tells me the categorical options are Y and N for yes and no. So this sort of data dictionary is so helpful if you're working with an analyst on your project. I mentioned coding. Coding in your data set is often used for categorical variables that you may want to add a shorter version of whatever the answer is. So in the example of death, Y or N. In the example of the mosquito trap zones, it's 1 or 2. Now, a preferred coding style would be that if it's a negative or a positive or a no or a yes, negative, no are generally 0. 1 is generally yes or true or positive. In the case of case status, if you have an unconfirmed positive and a confirmed positive, you can have 1 is unconfirmed, 2 is confirmed. That means that 0, 1, and 2 are in the correct order as far as how sure we are that they are positive. As I said, you need something to indicate that the cell does not contain data. So I prefer NA, which means not available, but it is read by most statistical programs as an empty cell. Some software reads blank cells as 0 rather than blank or missing. So make sure that you use a value. Could be NA, could be none, could be missing. Do not use blank if you want to make sure that your software is reading in appropriately that there is no data in that cell. Frustrating thing for me, in some software, it is considered normal that 99 or 900 indicates a missing value, and maybe 89 or 800 would indicate an error. This is not preferred because if your analyst is rushed and doesn't have time to look at the data first, remember, you should always look at the data first, but if you don't have time, you're rushing and you want to get some quick results out, you may have 99 reading as a number, and that's a problem. So I prefer NA, but also using just none or missing to make clear that there are no data there, and there is a reason for that, rather than having a blank cell or having a number that might be misread. Data cleaning is something that you or your analyst will have to do in the course of the analysis. The first bit of data cleaning is looking through the data for transcription errors. These are often things like misplaced decimal points, misspelled words. If you can, in your data entry, make sure that anything that requires spelling, where you have set categories, that you're limited to just the categories that you have. Otherwise, spelling can be a problem. County or state, people will use different ways of writing, either all capital or sentence case or capitalize every word. Software programs read those as different things. So transcription errors are aligning all the data and making sure that everything is where it should be. Data cleaning also looks for missing data, especially checking for if there are variables that are very missing, we may not want to use those in our analysis. It will look for out of bounds data. So out of bounds data are numbers that really don't make sense. This is like your 110%. This is your values from a CBC Chem that are not consistent with life. So data that you say that can't possibly be true. Be aware that sometimes what looks like out of bounds data may actually be a true data and just an outlier. So if you find what you think is an out of bounds data point, go back and check in any way that you can what does that actually come from. And then some other data cleaning. The first thing you're going to do is look at the data. So you're going to make some summaries. You're going to look at the ranges of the different numeric values. You're going to look at the counts in the categorical values. And then you're going to visualize. So cross-tabulation is where you take one variable on the columns and one variable on the rows, and you cross-tabulate to see how they align with each other. Cross-plotting is where you put one variable on the x-axis and one on the y, and you can see how they align with each other. This can be very good for logic checks. So we're looking for out of bounds variables. So variables like those 99s that indicate missing that show up in a numeric where we're supposed to be on the 0 to 1 range and we've got a few 99 stuck in there. Okay, well, we need to go fix that. We're looking for, do we have the same number of values for each variable? So is there anybody missing any of those variables, and are they aligning properly? And then we're looking for illogical results. So a great example is that the number of live births should not be greater than the number of pregnancies. If we're talking about litters, you can have the number of offspring greater than the number of pregnancies, but the number of live births should not be greater than the number of pregnancies. So that allows you to check. Is this logical? Are we having some weird issues? I have had, as an example, if the person reports that they are not a smoker, they should not have number of packs smoked in the last month. It should be 0. So if we see a value for number of packs smoked in the last month, but they're recorded as a non-smoker, that's an illogical thing. We need to check that. We need to go back and fix one of those variables. When you're sharing your data or when you're collecting your data, you need to think about storage and you need to think about data security. So for storage, I abide by the rule of 3. The rule of 3 says that you have one local data file that is active. That's the one that you're actually working in. You have another one locally, either on a folder that you're regularly using or on your laptop or desktop, that is secure, meaning you're not touching it, it's just a local backup. And then you're going to have one offsite backup. This might be in the cloud, this might be on a data stick or an external hard drive, and that should be secure. So that should be in a place that's not stored at the same place as your computer, that is held safely somewhere, so that if something catastrophic goes wrong with your local system, you will have a backup available to you. For security, you want to limit access to the people who need access to your file. Every person with access to your file is a potential security risk. This is not to make you feel paranoid, it is simply to say that you need to make sure that the people who have access are the people who need to have access. If your data are in a physical file, you need to think about the physical location, and if they're on your laptop or on an external hard drive, you need to think about the physical location of that as well. Make sure that your physical location is secure, it's locked. If you have it in a digital location, ask yourself, is it password protected? If you are working with human health data, is it HIPAA compliant? Make sure that your data are stored in a digital location in which people cannot accidentally or on purpose erase or manipulate the files. Then finally, privacy. We have to think about confidentiality. So we have to think about making sure that our participants cannot be identified from the data that we are storing. And one of the ways we do that is called de-identification. This is where you remove any PII, which is personal identifiable information. So things like birth date, address. What is considered PII may vary based on what we're working on. So, for instance, when I work with a data set that's primarily in the Chicago area, zip code is not considered PII because there's a lot of people per zip code in Chicago. When I'm working with data from Southern Illinois, we go to the county level because zip code is a little bit more identifiable. If you are doing de-identification, you may have a key. because you may want to be able to re-identify the data. Say you have a participant who wants their data removed from the study, or you want to be able to contact a participant, you will have a key to be able to identify who that participant is as the project manager. But that key needs to be offline or encrypted and or locked. It needs to be somewhere that is completely secure, highest security. When we're de-identifying, we also have to worry about what's called deductive disclosure. That's where you've removed all the PII, but people could still figure it out based on the clues in what is technically not personally identifiable. In this case, we may limit our reporting. We may use aggregation. So we often use decadal age range, so 0 to 10, 11 to 20, rather than the actual age. Or we may use county rather than zip code, or state rather than county, or region rather than state. And then sometimes we do jiggling of information, especially with mapping. We may add random numbers to the latitude and longitude of the location so that we don't identify a person's home address. When we're creating a map, we may add a little bit of fuzzed data to any variable so that we are not sharing too much information. Whether or not you need to do that is something that you should really discuss with your IRB or with any other organization that is helping you with data security, or talk to a data manager or a statistician who is familiar with working with private data. When you're thinking about data storage and long-term data storage especially, you need to think about the format. So one thing you need to think about is whether it is open or proprietary. So for example, Excel is proprietary software, but CSV is open software, which means it can be read by multiple programs. You need to think about how much support it has. So for instance, SPSS outputs can only be read by SPSS, whereas again, CSV files can be read by almost any program that works with data. When you're thinking about compression of images, you might want as low compression as possible. So in general, you want to save your data for the long term in formats that are more preservable, meaning that they're open source, they're widely adopted, have a lot of support, and have less loss or compression and no embedding of content. When you're documenting your data for storage, you want to document how you collected the data, what's the context and the methodology of the collection, what is the structure and organization of the data files. This is where your data dictionary comes in handy. You want also any reasons for missing values, and you want to define any jargon or acronyms that you might use in your data. You might say, well, I know what those mean, but if you're going to ever share, or if somebody after you is going to come along and look at the data, you want it to be clearly understandable by those people. You also want to document any data validation and quality assurance you've used, what format your files are saved as, and what software you've used to analyze or to otherwise manipulate them. Any analysis you want to document, so any algorithms used for transformation, any calculations that were done, and then finally, you want to document how confidential they are, who has access, and what are the conditions for use. There can be sharing of data where you can limit it to non-commercial use only, or you can limit it to use but with attribution, so you can document that with your data. And then metadata is the term that we use for anything pertinent that we need to understand the provenance of the data, meaning what do I need to know to understand what these data are. Different fields have different standards for metadata, but in general, the metadata should include what would be necessary to recreate your data file. And when you're describing your data for sharing, you need to describe the format. So what format, what type of file is it? What type of data it is. So observational data are the capture of data in the clinic, in the lab. This is usually irreplaceable because it's only the data that you collected at that time, and you can't go back and recreate the exact conditions of the clinical trial. Experimental data from lab studies is in theory replaceable, but in practicality, it may be very difficult because of cost. Simulation data is data that are generated on the computer. The inputs for simulation are more important than the outputs usually, because if you have the same program and the same inputs, you should get the same output. This may not be true with generative AI, but in general, if you save the inputs and the program and the exact version of the program that you used, you should get the same output. Derived or compiled data are data that you gathered from other sources. So maybe weather data, maybe census data. So you want to record where and when you got those and any other manipulation that you might have done to compile them and to add them to your data. And then analyzed data are the publishable format. So these are your tables and graphs that you're adding to your manuscript. And of course, you have the metadata, which we use to describe where the data came from and what it would take to recreate it. Now, data sharing may be required either by your funder or by your publisher. This can be limited by ethical considerations. So you are not required to share your full data set if there are personally identifiable information in there. You can do a de-identified limited data set for data sharing. The methods for data sharing, preferably you have an open source repository, some sort of data bank where you can deposit your data. Alternatively, you could have a limited access folder on a network, say a public box folder where people can have an access link where they can get in and download the data but not manipulate it. Or you could have a data available by request. I will tell you from people who work with data and open science, they generally consider data available by request, email me for data. They generally consider that to be not shared data, because frequently people will say data available by request and the data will not actually be available. Also, it's a lot of work on you to provide the data to people who want it. So better to use an open source repository or a limited access folder with whatever sharing considerations you have. Now, things that you can consider with data sharing, you don't necessarily have to share all of it. I generally share the data that were associated with the paper that I am publishing at the time of publication of the paper. So not all of the data, just the data that went into that particular publication. This is where having good documentation and metadata is helpful, because if you have your data dictionary and your metadata file already, you can share it with all of that, and then you don't have to explain anything about the data after you're already done with the study. You can, again, put permissions and parameters for use around the data so that people can require a data use agreement or have to agree to non-commercial use. And then reporting and notification can be added onto it. So this should have given you everything you need to know about basics of data management and data sharing. Again, I encourage you to talk to experts. Your institution may have a research data service or data management service that would be able to help you find the solution that's best for you. And of course, if you're working with a statistician or an analyst, which I highly recommend, talk to them about what their preferences are and how they want the data formatted and what the data dictionary should look like. That will help you make sure that as you collect the data, you've organized it in a way that makes it most useful to you and your team. See you next time.